All right, welcome to tutorial 6. We're going to talk about firms and production here. So we're just going to walk through the main topics and then get into the details. So first we're going to start with just a general overview of how we model firms' decision making. We'll talk about what inputs mean. We'll talk about the production function. We'll talk about time and how costs and firms' decision making varies over different time scales. The law of diminishing returns, you've probably heard of this or seen it before. We'll just overview that. We'll introduce the idea of isoquants, which is essentially the firm's analogous indifference curve. So we're going to hold quantity constant and we're going to vary the inputs and look at how varying inputs across two dimensions gives us a constant quantity of output. We'll talk about the marginal rate of transformation, marginal rate of technical substitution, which is essentially how we talk about the slope of the isoquant. And this is analog to the marginal rate of substitution for the consumer. Then we'll talk about some elasticities. Returns to scale is sort of a technical way of describing how changes in how scaling up inputs scales up output. And then we'll briefly touch on technological change. Technology is more of a macroeconomics topic. I wanted to introduce it here just to give you a sense of what it looks like, but we're not going to talk about it in detail. Okay, so first we're going to start with firm decision making. This is really just introducing the way we think about firms and how they choose. So really just a firm is sort of a collection of people and resources, sort of a unit of decision making. This is pretty general. We do this on purpose because there are sort of many types of firms. The way we approach firm decision making is really sort of stylized in a lot of ways, but it gives us sort of an entry into firms' decision making, which gives us some traction. And later on, as we go, we'll maybe talk about different ways of viewing firms. But this is really where we're going to start. That firms' goal is to maximize their profit. So this profit maximization objective is very crucial to everything we do with firms. And the way we describe profit is we denote it with pi. And you might have seen this in your intro. But really, this is just the difference between revenue and costs. We're going to talk about costs a little bit more in the next chapter. But here, revenue is just the price that the firms are selling at, and we multiply by quantity. So we add up every unit that the firms are selling, and we multiply that we multiply it by price, which gives us our revenue. So every unit at the price. And you've likely seen this before. So I just wanted to include this line here that the profit maximizing assumption isn't always true, but at this point, it makes our lives a little bit easier. So we're going to treat firms as sort of this almost generic decision maker for the time being. This is an assumption. And I wanted to point that out here very early on. This simplifies our lives quite a bit when we model firms. But so when we think about firms' profit maximization decisions, really this is what's required is that firms are producing efficiently. So they're not throwing away resources. So when we sort of think about in the background that firms are aiming to be as efficient as possible. So when to model efficiency, we need some concept of production, and that's when we turn to production functions, which take inputs and transform these inputs into outputs. So we're using technology and a production process, and we're going to sort of stylize this into what we call a production function, which we often denote with a lowercase f. And there are sort of three main categories of inputs. The first is capital services. So this is these are things like land, buildings, machines, factory resources, anything that we can describe as capital. We also have labor inputs. This is really just everything coming from workers. So if it's something that a human is doing, then that's a labor service. And this can be at every level of human input in a firm. Everything from someone working behind a counter to the CEO. These are all labor services. And lastly, I just wanted to note this here. Materials are sort of the raw inputs. We don't typically use these in the production function. And the main reason is we're sort of taking these as given. We don't, when you're producing something like a loaf of bread, you can't really, there's no real like trade-off involved. When we talk about labor and capital, there is sort of an interesting relationship between capital and labor that we have to make decisions over. But when you're when you're producing bread, you already know generally what the inputs are required for the bread. It's a recipe. So when we're modeling firms, we typically look at only labor and capital, these two. So you basically will never see materials as part of our model. I've included it here just to sort of note that in the background, materials are included in the production function. But because there's no trade-off involved, and because economics is about trade-offs, this ends up sort of complicating our models in ways that aren't useful, at least at this level. Okay. So we have our production function, which takes capital, labor, and materials and spits out for us some quantity. And this is a quantity, for the moment, we're going to talk about quantities as one-dimensional goods. But later on, we will possibly introduce sort of a vector of quantities, which is essentially just like a firm that makes more than one type of thing. Okay, so in the short run, firms can adjust their output. the way we define short run is that there are inputs, at least one input, that we cannot adjust. But this doesn't mean we can't adjust output in the short run. In fact, we can, and we're going to be modeling short run decision making as it relates to quantity. Short run is just defined as a time period on which you can't adjust everything. And often the way this is modeled is that we can adjust labor in the short run and capital and labor in the long run. But typically it's sort of spelled out for us when we approach problems. Okay, so what we say is that a fixed input is an input that can't be adjusted in the short run. So we have at least one fixed input in the short run. Everything else is what we call a variable input. Okay. So let's turn to short run production. So in the short run, typically we say capital is fixed. And labor is variable. So changing output involves changing the labor input. So we often write our production functions in the short run like this, where we have labor, which is variable, and we have capital with this bar over top, sort of denoting that it's a fixed quantity. So we have fixed labor input, fixed capital input, and variable labor input. Which gives us the total product of labor, sort of by definition. So the marginal product of labor is just, by the name you might be able to anticipate where we're going with this. It's just how quantity changes when we change the labor input. And to capture this, as you've probably come to expect in this class, we use calculus. We just look at the derivative of the production function with respect to L, our labor input. And that tells us how the production function changes when we change labor. And I'm just including a bar over the top of capital, but it doesn't actually need to be there. Okay. So we have the marginal product of labor. We also have the average product of labor, which is just output divided by the number of labor inputs, whether this is in terms of hours or salaried workers, just some measure of the labor input. Okay, so we'll use these two definitions as we go through, particularly in chapter, chapter 8. Okay. So next we turn to the law of diminishing marginal returns, which isn't really, it's not a mathematical law. It's really just a fact that we see show up in the real world quite frequently. It isn't always true, but it's very consistently true. So the idea is just that when we increase our labor inputs, so on the right here, as we increase our labor inputs, we increase our quantity of output. So as we increase, as we go left, as we go right, we increase our quantity output. So we have this positive relationship as you would expect. But at the same time, the increase is getting smaller. So as we move up this production function, the slope, which is the rate of increase, is getting smaller. So the production function is getting flatter as we move towards higher labor input. So on the left-hand side here, we have this the marginal product of labor, which is the first derivative of the production function with respect to L, which, as you can see, once we start moving past this point, this L hat, the rate of increase becomes smaller. So for a while, we had an increase that was getting steeper, and then after L hat, the increase became flatter, which is represented by this curve here. So for a while, the slope is getting steeper, which is represented by a higher marginal product of labor. But then for a while, after L hat, this the increase of the production with respect to the labor inputs is getting smaller. And this is the law of diminishing returns, that there's some point, L hat, where this happens, where we switch from increasing the marginal product of labor to decreasing. Okay, so we can also look at the derivative of the marginal product of labor with respect to L, basically showing that this derivative is negative. And you can see that from the graph here, that at some point after L hat, we start to decrease the marginal product of labor. At any point before, of course, this is, we're still increasing. But after L hat, we start to decrease. So we're basically just saying at some point it's going to be negative. Okay. So we have this this production function. We also, when we think about production functions, often we model these with a Cobb-Douglas, which you'll be familiar with from our discussion of utility curves. Isoquants are the equivalent of an indifference curve. We're saying, using some production function, we're going to choose some given quantity, Q bar, where we can vary our inputs, but we're holding this quantity constant. This tells us the relationship between the inputs to give us Q bar. So as you can just sort of intuitively look at this, as we increase one input, we have to trade it off with the other input. So we're decreasing the other input, which is very similar to what you would expect with an indifference curve. And really, this the intuition for isoquants is very similar to that with utility curves, excuse me, indifference curves and utility functions. In the background, you should be sort of rhyming this with our discussion of utility curve, which is analogous to the production function, and the isoquant is analogous to the indifference curve. And all of the standard assumptions about indifference curves also hold for isoquants. So first we have, when we move the isoquant farther out, it's more preferred. It's a higher quantity bundle. 2, that isoquants don't cross. 3, that isoquants slope downward, which captures the trade-off between capital and labor. And isoquants can't be thick. So essentially, any movement in either direction puts us on a higher isoquant, or lower isoquant, depending which direction we go. Okay. So this looks identical even to some of the indifference curves we've already worked with in this class. Okay. And just like with utility curves and indifference curves, the shape captures something about the substitution between inputs. So this graph on the left here captures what we call perfect substitutes, where for every input x can be substituted perfectly with some level of input y. This second graph here is perfect complements, where we need to increase both a and b at the same time to move to a higher isoquant. Okay. So when we think about substituting, the slope of the isoquant is what we call the marginal rate of technological substitution. And this is the analogous concept to the marginal rate of substitution for the consumer. So essentially, we're just looking at the indifference curve for the consumer, or we're looking at the isoquant for the firm, and we're saying, what's the slope? Can we characterize the slopes across all LK combinations? And the way we do that is just by taking the derivative of the production function with respect to L. And when we do that, because there are two inputs in our production function, we first have to take the derivative of the production function with respect to the first, and then with respect to the second. But because the second depends on L, because K is a function of L, then rearranging, so we have to multiply the derivative of the production function with respect to K times the derivative of the production of K with respect to L. Then once we do that, setting it equal to 0, we can rearrange to give us this relationship here. So these are just rules of derivatives. All we're saying is that to stay on a given isoquant, we have to set this equal to 0. So we're not moving our quantity. We're just trading off between K and L. And we know that there's a relationship between K and L, so we have to model this explicitly, which gives us this derivative here. And then all we have to do is rearrange. So what's nice is this comes out to be a relationship that, again, rhymes with the marginal rate of substitution, where on top we have the derivative of the production function with respect to one good, one input, and on bottom we have with respect to the other. And this is really just the slope of the isoquant. Okay. So the same sets of techniques that we've used for consumers, we can apply here to firms, and hopefully this is giving you good feelings. Okay, so the elasticity of substitution is really just the idea of substitution across our inputs So here, we're using this notation here just because we're in the world of firms. All we're doing is taking the derivative of k over L with respect to the marginal rate of transformation. So we're just looking at the marginal rate of transformation and looking at how it changes with our capital labor ratio. And then we just multiply it by the ratio. So this is our standard elasticity measure applied to the change in the capital labor ratio when we change the marginal rate of transformation. You'll remember our standard elasticity measure is just the derivative. So when we talk about the price elasticity of demand, we talk about the derivative of the demand curve with respect to the input variable price. And then we multiply by price over quantity. And that's sort of the equivalent form to what we're doing here. Just the responsiveness of the capital labor ratio to changes in the marginal rate of transformation. Okay. So we're going to talk about the returns to scale here, which is a way of characterizing how production functions change when we scale up the inputs. So the isoquant tells us sort of the trade-off between L and K, but what happens when we move both at the same time? How is Q responding to sort of simultaneous increases in L and K? So we have three cases. The first is what we call constant returns to scale. So when we double the inputs, when we put a double up front here, in front of the inputs, we're doubling our output. Increasing returns to scale is just saying when we double our inputs, we're going to more than double our outputs. We're saying when we double our inputs, that's greater than a doubling of our outputs. And when the inequality goes the other way, doubling our inputs is not as good as doubling our outputs. And this is in the homework. Essentially, this is just a way of capturing how the production function changes when we scale up our inputs. Another way of saying that is, how does our quantity scale with our inputs? Okay. And lastly, before we close out here, just a note on technological change. This is more of a macro topic, but we can put some variable, often called A, out front of the production function. So we can, sometimes we write this as A as a function of T, which sort of measures changes in our technology level over time. So we can vary time, increasing from 0. And when A increases, then our output per input also increases. So all we're doing here is just increasing our capacity to produce, increasing our technological abilities and our efficiency for our inputs. We really don't talk about this much, especially not the changes over time. If you're interested more in that, there's a lot to talk about in intermediate macroeconomics. It's one of the big topics there. But it's a little bit outside the scope of this class. But it's a pretty fun topic if you're into it. So I just wanted to note, so up here, when we talked about our Cobb-Douglas production function, we included an A, which sort of A often represents, just in notational world, a level of technology. So I just wanted to point that out here. But in this Cobb-Douglas world, A is just a constant. We don't really model it dynamically. Okay, so that's all we have here. In the next chapter, we're going to talk about costs in a little bit more detail. So I'll see you there.